Thank you very much for staying until this late. I know it's very late in the evening, but our friend from Australia is already reaching nighttime. I think it's 8 o'clock. Professor Brian Schmidt. He's a Nobel Laureate. I don't think I need to introduce that he's a Nobel Laureate. And he was supposed to come here for this conference, except that because of the heightened COVID situation, we had to postpone this conference to a later date. And as the president and vice chancellor of the Australian National University, he finds it very difficult to reschedule some of his appointments in Australia. So I don't want to read too much into his CV, except to say something that Brian is actually a very good maker of wine. He owns a vineyard in Australia, just outside Canberra. And, oh, he's there. And it's easier to sell, he said, he quipped once, that it's easier to sell your wine when you have a Nobel Prize. So Brian, please, the floor is yours.
Hello, everyone, and nice to meet you all. I am sorry that I am not there in person. I will actually be in Singapore next week, looking at your entire university system with the Ministry of Education. But unfortunately, I was unable to lengthen the trip due to all the things that I have to do here at the ANU in my role as University Vice Chancellor and President. But it is, I thought it would be good to reflect a bit on the life of Prof Yang, as this is, of course, his birthday. And it's worthwhile thinking about the 100 years of physics that has existed during his lifetime, because he has literally existed for the entirety of modern physics. And it's quite remarkable if you think about what was happening during the life of his and the absolute seminal role he played in getting physics to the place that it is. So I'm going to share my screen and bring up a small number of slides that I'll talk through. And I'll try to, at the end, be a little provocative about just physics, the state of physics relative to 1922 when Prof was born. So hopefully this will go. Let's see. All right, I can see my screen up there, so hopefully everyone can have it there. So again, I think 100 years of physics, you realize just how much has happened during Prof Yang's time. So let's go back to 1922. On November 9th, 1922, so this is 40 days after Prof Yang was born, that is when both Niels Bohr and Albert Einstein were awarded the Nobel Prize. Let's start with Albert Einstein. Albert Einstein was actually awarded the Nobel Prize for 1921 in 1922. It wasn't actually awarded in 1921. They decided they didn't have anyone they wanted to award it to in 1921 and waited till 1922. And that, of course, was not for all of the remarkable things in relativity, which I'm deeply connected with in my research, but rather for the photoelectric effect, one of the key instigators of the field of quantum mechanics. And of course, Niels Bohr won it in 1922 for the work he did at the beginning of the structure of the atom and radiation, all related, of course, to the beginnings of quantum mechanics. So he was there very much at the beginning of those fields of quantum mechanics, which of course got going in his first early years of life. But in 1922, I want to think about probably the big scientific work that happened that year. And that was born out of general relativity, which the Nobel Prize Committee made very clear was not what Einstein was awarded his Nobel Prize for, relativity still being very controversial, despite it being demonstrated more or less by Eddington through an eclipse expedition done in 1919. So the emergence of general relativity in 1919 led in 1922, after this event that made Einstein famous, much more so in the public community than the photoelectric effect. But it allowed Alexander Friedmann to do his paper, which is essentially the Friedmann model of cosmology, the model where when you start with an isotropic universe, something I suspect Friedmann chose because it was easy to solve, rather than him having any reason to believe it was necessarily true. And from that, he derived the notion of a dynamic universe, one that I don't think they would have described as expanding, but one where the notion of something like redshift existed, and the notion that depending on the density of the universe, you would have a universe that was closed, that is bound in time and space, one that was open, that is hyperbolic geometry and unbound in time and space, and the flat universe, which it would appear that we live in, of which, and those three solutions are the three solutions that I was taught, and indeed the three solutions I tested against with our team in 1998 when we were out measuring the distances and redshift relations of supernovae. So that was born in 1922, and indeed, while it was submitted in June, it was published in December. And as I said, those solutions to a homogeneous and isotropic universe exist with us today. And that, I guess, is, from my perspective as a cosmologist, quite an interesting coincidence with C.N. Yang's birth. If we then march forward, of course, we had all of the birth of quantum mechanics during the 1920s and early 30s. And C.N. Yang, as he grew up, suddenly is, after the end of World War II, going into what arguably is an incredibly exciting time in physics. But if you think of the advancement of nuclear physics and quantum during his childhood, there was a huge amount of things that ended up creating what we would describe as, sort of what we would teach in first or second year physics today of quantum mechanics, starting with de Broglie, Heisenberg's, Schrodinger and Dirac's equations, the discovery within nuclear physics of the neutron and positron, Fermi beginning to understand nuclear reactions and how neutrons can affect nuclei, Lawrence with a cyclotron going through and being able to manipulate nuclear and create nuclear reactions, and a whole range of experiments that became more and more sophisticated over time. So C.N. Yang, after finishing his master's degree at Tsinghua, came to the United States to meet a whole bunch of people who, of course, had been intricately involved in nuclear physics behind closed doors as part of the Manhattan Project. And he was very keen, of course, to work with Fermi, but as a foreign national, he was not able to work with Fermi, but nonetheless started his efforts in graduate physics as an experimentalist, which is, I think, by reading various things, was perhaps not where he was most strong. But he already started what he is known for is bringing group theory and particle physics together under the supervision of none other than Teller as a theorist after he sort of gave up on that experimental nuclear physics part of his life. Now, as someone who got to meet Teller as a graduate student, I think this was in Teller's era of being, I would say, a slightly more grounded physicist in 1948, I think, when Prof Yang finished his PhD. For me, my meeting of Teller was him asking me if we could find him an outbound comet that he could blow up with a nuclear bomb. That would have been in the mid 1990s for me. So of course, CN started quite a remarkable time in physics in motion. I would say he started where physics got hard. Really, I guess in 1954 with the Young's Mill theory, but I guess started, that theory was a little before its time because a few things weren't known, but in the weak force parity violation in 1956, it sort of broke a number of pre-held misconceptions by the entire community that then unlocked, I think, a revolution that essentially led to the standard model. And it's worthwhile thinking about just how important he was in that, because the Yang mills used essentially non-abelian groups and gauge theory to look at how particles can be force carriers is essentially the foundational theory behind all of the developments that followed. But it took a little while. First of all, this is the great surprise of parity violation that really took everyone by surprise in 1956, but led, well, I guess it was 57, by the actual experiment by C.S. Wu, who unfortunately did not get credit for her amazing experimental work on it through the Nobel Prize. But nonetheless, this was the revolution that started the ball rolling. The realization through symmetry breaking that you could actually use the Young's Mill method on massive particles rather than massless particles really started in motion the ability for Glasgow to unify electromagnetism and the weak force. Very soon after, of course, the Higgs mechanism was proposed, and those things allowed Weinberg and Salam to essentially unify in the final form electromagnetism and the weak force. And with the addition of asymptotic freedom, we ended up with the final three-force unification, but essentially under that 1954 Young's Mills basic concept and framework for how you might do that. It took a long time, of course, to actually show that this work done in the early 1970s was the standard model and was largely correct. And it was through the quite quick measurement made possible in 1973 of weak neutral currents and the discovery, once we got a large enough accelerator of the WZ bosons in 83. Better and better accelerators allowed the top quark, the tau neutrino, and eventually, well, the tau neutrino came through other experiments, but the Higgs boson, of course, finally in 2012. So an incredibly strong time for particle physics, but it leaves us, I guess, in 2022 with a quandary of what's next, and we'll think. I'll talk a little bit about that towards the end. Of course, other things happen beyond just particle physics. We've had a revolution during this time in condensed matter physics and solid state physics that's led to remarkable technological advances, and essentially us being able to understand within materials and substances, quantum mechanics, and how that manifests in ways that are ultimately useful in everyday lives. The development of masers and lasers in the 50s and 60s, essentially quantum optics, superconductivity coming through as sort of its own little piece of work in the late 50s, and novel things like Bose-Einstein condensates, again, emerging out of a mixture of fields, but ultimately to our understanding of the foundations of physics done many, many years earlier. So these are all things that continue today, but they are maybe not quite the glorification of a unified theory of everything, but rather of specific novel instances of how physics works in materials here on Earth that create all sorts of possibilities of technology. Now, a sidelight during this time was the advancement of astronomy and cosmology. When I started my PhD in 1989, there were people talking about the connections between astronomy and particle physics, but they were a very small group of people who were on the fringe of the field. And a lot had happened, of course, during this time in astronomy related to the astrophysics, including pre-World War II, the work by Bethe and Chandrasekhar that really underpinned the workings within the nuclear reactions and structures of stars. And it wasn't just Bethe and Chandrasekhar, but they were at the very forefront. That work actually happened in the 1930s as well. Quasars, and then post-World War II, a lot of taxonomy and stamp collecting occurred with the new large telescopes, the 5 meter at Palomar. But I think one of the first real foundational physical breakthroughs was the detection of what we call quasars, quasi-stellar objects, that were sort of beyond imagine in terms of the implied amount of mass within a very, very small area. They were literally a 10 to the 12 times brighter than normal objects, and were yet still stellar in appearance, which meant that they were very small indeed. And they were postulated to potentially be supermassive black holes, something that, of course, was emerged from the Schwarzschild, one of the first solutions of general relativity. But just because general relativity allows things to occur does not mean that they actually occur. And the fanciful idea of these ideas of singularities in space-time was, I guess, a fair bit for people to take in if you think about back in 1964. Yet, the detection of quasars was the first hint that they were real. Also in 1964 was the detection of the cosmic microwave background. That detection of the cosmic microwave background, an afterglow of what we call the Big Bang or the early universe, has evolved to become probably cosmology's and astronomy's most precise way of understanding the universe. And it's worthwhile reflecting that in 1964, that Dickey and Peebles had sort of done a theory that predicted that this might well be there and to go out and look for it. But it was actually a theory that was a rehash of a theory done by a very comically authored piece of Alpher, Beta, and Gamov in 1948, which had run a similar, although less sophisticated, set of calculations. And I'm not sure which one of alpha, beta, and gamma was. I think beta may have been added as the joke, but alpha and gamma, I think, were the two behind it. During late 60s, throughout the 70s, there was, and even going back to the 1930s, evidence of dark matter. That is gravity, the evidence of gravity without associated baryons or atoms, as astronomers will typically measure. And that has slowly accumulated over time, becoming stronger and stronger over time. Everywhere that astronomers look throughout the universe, there is evidence for something that seems not to be atoms, but has gravity. And the evidence has come in longer and broader ways over time. In 1979, again, another part of general relativity, the notion of gravitational lensing, strong gravitational lensing, was detected. That is now a very useful tool to look through and have a way to magnify the early universe, but also to map things like dark matter in massive parts of the universe. In 1992, the anisotropy, not due to the essentially Doppler shift of the Milky Way's motion in the universe, was detected. These anisotropies are related to essentially the growth of structure in the very early universe, roughly 380,000 years after the Big Bang. And they allowed us to start making precise measurements as we were able to quantify better and better these measurements. One of the interesting things about these anisotropies is they indicate effectively a seeding of structure in the very early universe. That is, you can't create, you have to essentially create a scale-free set of perturbations in the early universe, which then get amplified by gravity over time. And that is in line with what would be expected from quantum fluctuations in, for example, a rapidly expanding universe, often referred to as the inflationary epoch. In 1998, a team and another team, the team I was involved in and another team led by Saul Perlmutter, made the unexpected measurement of cosmic acceleration. The universe was not decelerating as expected, but rather in total, it would appear that the total gravitational effect of everything in the universe was one of acceleration, indicating that the most predominant things in the universe had to have something like a negative equation of state where gravity became essentially repulsive as opposed to attractive. Now that, of course, was something predicted in 1917 by Einstein to try to make the universe static, a mistake, but something that he held on to for quite a while. And that notion of the cosmological constant as formulated in 1917 has been used as a panacea to fix all sorts of problems in cosmology over time, always to be shown wrong. And so I can tell you in 1998, when we made the measurement, we were kind of scared because we knew that it had been a mistake many, many other times in history. Yet, as we have made better and better measurements, the evidence for acceleration has gone from being strong to incontrovertible over time. And no stronger than from the very precise measurements made of the anisotropies in the cosmic microwave background, starting with the Boomerang and Maximum experiments in 2000, which saw the first, what we call Doppler peak. This is sort of the largest scale of amplification, of gravitational amplification in the universe, and gives you essentially a cosmic ruler that allowed us to measure the curvature of space in 2000. And it was that measurement in 2000 that made me suddenly think that our 1998 measurement of acceleration had to be correct, because it was almost impossible for our measurement and that measurement of the universe being flat to be reconciled unless there was something like a cosmological constant in the universe. Those precision CMB measurements have persisted, WMAP in 2003, and then Planck more recently, providing higher and higher signal to noise and higher resolution maps of the universe. And what's quite remarkable is, as those measurements have become better and better, the data has effectively just zeroed in on that initial measurement made in 1998 by us and the 2000 measurement by Maxima and Boomerang. Another thing, again, out of general relativity, gravitational wave detection in 2015. That was something, of course, that took many decades of hard, laborious, precise precision measurement with laser interferometers. And I have to admit, I could see it coming. I was on one of the governing boards for LIGO, but I was surprised it happened quite as fast as it did. Now, partially that was because the sensitivity of LIGO maybe came on a little faster than I did, but also it would appear that gravitational waves were happening a little more frequently than a conservative estimate would have expected in the universe. So there were nearby objects that had a lot more mass than perhaps one would have naively expected. That is that the merger of black holes was, at substantial mass, let's say 20 or 30 solar masses for each black hole, was happening at a rate, sort of not quite an order of magnitude higher than I would have thought, but certainly as several times. So that is a new area that is just at its infancy, and we're going to see a huge way of, again, making precision cosmological measurements over time, but just understanding how the universe evolved to create these supermassive black holes, but also this very large population of, massive compared to the stars we see in the universe today, but not galactic-sized black holes. Of course, most recently, we've been able to go through experiments at our galaxy center in the center of a nearby galaxy, M87, and in our own galaxy, able through precision measurement of the orbits of stars, demonstrate that there is a supermassive, several times a million solar masses, black hole in the middle of the Milky Way, and be able to see some of the relativistic effects caused by that. And then the rather dramatic images of black holes and the shadowing caused by the warping of space-time around their accretion disks, where material is being heated up and emitting in synchrotron radiation, first around the largest nearby galaxy, M87, and then just recently, the center of our galaxy, what we call Sag-A star. And interestingly, again, in the case of Sag-A star, the measurement completely consistent with the orbital determinations of its mass, which is nice to see. Although there's still, I would say, some ambiguity of exactly how unique the images created, especially for the Milky Way black hole is. But there will be more and more of that coming along over time. I think it's also worthwhile thinking about the rise of computational approaches, and that started back in the Manhattan Project with von Neumann creating essentially computers that could go through and start doing the calculations that were just impossible to do of complex systems. It's brute force, but it is becoming more and more effective over time. That allows us to create designer molecules, materials, and other things by literally just brute forcing the quantum mechanical calculations that were not possible otherwise. That allows us in astronomy to do the simulation of how stars work and their convection, but also how ocean currents and climate works. It allows us to create weather forecasts that are just insanely good to what was possible in my childhood. It allowed us to go through and simulate the merging of black holes and neutron stars and see the chirps that emerge. And that was something that was not tractable as an analytic calculation without the computational approaches. And they, of course, got those just right, which is, I think, quite remarkable. But there's other types of computational approaches in almost any and all areas of physics. And it doesn't mean that having a strong theoretical mind to go through and look for general analytic solutions is not important. It clearly remains important and will be foundational probably for us to do many of the unsolved problems that remain in our field. But it is something that has created huge opportunities of understanding things faster and quicker than I think ever possible. If we are able to start, for example, getting quantum computers to look at things like processes in molecules. So imagine nitrogen fixing being a classic idea of something that a quantum computer might be able to go. There could be quite revolutionary advances in the not too distant future, again, from even more novel computational approaches. And I think it is worthwhile just understanding how much that dominates what many people are doing in the world today. But there are big questions that remain. And one of the remarkable things that has happened during my life is that the big questions of cosmology and particle physics have almost completely merged. And so from 1989, where I have to admit, mildly amused by my colleagues who said this was the future, I have to admit they were absolutely completely prescient into what was going to happen. So open questions that we do not understand, baryon asymmetry. That is, why, given the equations of the standard model, are we here at all? We should expect all of the matter and antimatter to have annihilated and leave us a universe full of photons. And yet we see that there are, based on the cosmic microwave background, sort of 1 part in 10 to the 9 residual of baryons to the photons in the universe. Neutrinos remain an interesting sector within both cosmology and particle physics, and it's the sector that probably doesn't quite yet make sense of the things we know within the standard model. Why do they have mass? And this is a place where in cosmology, the neutrinos, we can actually test their mass. We provide some of the best limits, but at this point, we know that they're sort of in the lowest possible mass that they can have based on the other experiments, but it has not yet been definitively shown. We talked earlier around dark matter. Everywhere we look in the universe, there is apparently material, which I would presume is a particle, yet undetected and not really predicted, perhaps an axion, perhaps sterile neutrino, perhaps other things that remains enigmatic. It's not in the standard model in any sensible and easy way, yet everywhere we look is there. And I should say that the cosmic microwave background experiments pretty much requires, at a ratio of 6.5 to 1, a form of gravitating matter that does not interact with itself or with atoms. And I think many people like to discount dark matter, but I have yet to see in a sensible way to get rid of it within the cosmic microwave background. My own discovery with my team of dark energy remains probably even more enigmatic. We don't know what dark energy is, and we don't seem to have any way to really understand why it is there. It is almost like it is there without reason. And as I said, I wished I had a plan to figure out what dark energy is, but I suspect I will die knowing about exactly what I do right now about dark energy, but maybe I'm being pessimistic. Of course, there's still a desire to unify gravity with the other forces. That remains, something that almost every living physicist has wanted to see over the last 100 years. And again, cosmology provides perhaps one of the interesting ways to do that. By looking at the cosmic microwave background and looking for the so-called tensor modes, we might well be able to understand essentially the energy scale of unification of the where gravity is quantized. That seems to be the only conceivable way that at least I can think of about how we might get an insight. And we are really pushing the boundaries with experiments. Of course, we had a false start of perhaps seeing those so-called tensor modes, giving us that scale of quantization. But I guess dust, which is a problem for us astronomers. Some people like to study it. For the rest of us, it's a bane on our existence, got in the way. And so we will continue to see progress in that, but it will be more careful and measured progress over time. And finally, all of those things sort of predicate inflation, that is the measure of the cosmic microwave background, and for example, the whole theory of the cosmic microwave background. But what exactly is it? We do not have anything other than really a toy model of it. And that remains, I think, a really foundational problem that, again, maybe the Higgs mechanism gives a way of producing the inflaton, but we don't really know anything other than the cartoon model that we have. Finally, in my last slide, I think it's just worthwhile, and this is maybe, I am being pessimistic, but I think it is worthwhile to think about physics' role in society and how it's evolved. In 1922, physics was the king of science. And then during that era, the 1940s through about 1970, physics became not just the king of science, but something that was seen as just integral to the evolution of civilization itself, instrumental to humanity in almost any other way. We were kings every way. But since 1970s, physics public preeminence has been on the wane. We have, to the point now in 2022, physics remains, I think, the backbone of science, but we are often overshadowed publicly by big tech especially, but also areas of medicine. And I'm afraid the din of populism, which believes that science and the ability to actually go out and make hypotheses, test, and then extrapolate and make prediction is of limited use when you could just tell people what you know the answer is. And so I do believe we have a potential existential risk to physics, and that way I would say the advance of humanity and civilization itself, of not being able to attract the talent that physics needs to continually push the boundary and make the remarkable achievements which underpin most of the technological advance that we have seen across the world over the last 100 years, and create a world where lifespans now are beyond 70 years, and the fraction of the world that's been lifted out of poverty has risen dramatically. And I want to stop on that. Thank you.
Right, thank you, Brian. We today among the audience, we have some of the brightest kids around, brightest researchers, future scientists, and perhaps now the floor is open. You can ask your questions. Okay, before on the chat, actually we have online question. What can we do to revive the roles of physics as the king of science and instrumental to humanity?
Yeah, well, I think part of it is controlling the narrative. When it's not that physics isn't contributing to big tech, we're at the middle of it all, but we have been disintermediated, to use a language of big tech, by the people who take the ideas out of physics and make very large sums of money. And the challenge for physics is to somehow to insert ourselves in the public consciousness about how, if you're going to create Teslas or giant spinning disk farms or quantum computers, you do need physicists. And we need to create a compact with big tech, which is a long-term compact where we agree to coexist and not have, for example, big tech come and for short-term gain, steal large quantities of our talent, never to have them return to our fields again. And I do think that's happening more and more. And so we need to come into something where we can respect and appreciate and indeed coexist and use some of the amazing things that big tech can do, but not have them destroy the education and the foundational research, which will continue to provide the revolutions for future big tech. So I think that's a really important part of our future coexistence. And part of that is creating an environment that is attractive relative to big tech to be part of. And I think that in physics, we have had a very long-term sort of survival of the fittest approach. Work insanely hard, and if you're lucky in the top 5 or 10%, we will give you a job that will have much less certainty, much less pay than what you can get outside. And that has worked in the past, but it will not work in the future. So we're going to have to create, I think, an environment that people find more people find more rewarding for longer periods of time.
Well, there are a few more questions, but I hate the next question. Given that today we're celebrating the 100th birthday of CN Yang, but the question says, and I think on second thought, you have 50 more years to think about dark energy, actually. Should we continue upholding the CN Yang legacy even after his death to a minor modern twist? And I go on with the next question, which is similar. Should we replicate the early history of CN Yang via cultural and heritage programs?
So I think, I'm not quite sure if I exactly understand, but I'll take the question 2 ways. First of all, it is really important for us to understand the history of physics and how it's advanced, because humans ultimately do physics, and humans of 50 years ago or 60, 70 years ago are the same as humans today. And I think it's worthwhile looking at the amazing journey that CN Yang, coming from a war-torn country and being given an opportunity, clearly incredibly talented student at a very young age, and being able to come in to a country on the other side of the world, supported by that country, making sure that we use the talent of the world to solve the world's problems. And I do worry that we're going through a period of being more insular. We were insular before World War II. That made for a bad outcome. And we are going to a time now where we're being more insular. And so I do think understanding that history and what comes from it, and part of that history is the breadth of culture and backgrounds and how that contributes to making breakthroughs in these hard areas. It's not just going to be a small group and their friends. It is going to be people from around the world, and we need to make sure that we provide avenues for all of that talent. Think of the amazing talent, for example, right now, that's throughout Southeast Asia, around Singapore, but also emerging in Africa. And we know we're not yet tapping into that talent, and we need to all think about how we could do that in the same way that the United States did post-World War II.
Thank you. Any question from the floor before I switch back to the online session? No? Come on, you have the opportunity to ask a great man. Oh, okay, sorry. Now we have a high school student who is going to ask you some question.
Excellent.
Hi, so when you answered the first question, you said that you believe that with physics taking a back seat and like big tech and all the other more illustrious, maybe more monetized industries being in the forefront, you would lose a lot of talent. And you said that the approach of the past will not be able to be carried forward into the future. But so what I don't really see why that is in this case, because even if it's in the back, if you have to learn physics to even go into these fields as it's the backbone, then anyone who is passionate and interested about it would still somehow be gravitated towards the field over time, right? And also, it's with the increased interdisciplinary nature, is it so bad to be integrated into other fields?
It's absolutely fine to be integrated into fields. The challenge is that when a young budding physicist, or all of the young budding physicists, decide not to go do PhDs, but rather go and make $300,000 or $400,000 a year at AWS, Google, and Microsoft, doing incremental, essentially AI to run ads, something that they'll be very good at, that makes money. We don't get the advancement. We don't get that talent connected to the advancement of physics that will underpin the actual revolutions, right? So those companies exist due to a whole bunch of Nobel Prizes in physics. The problem is the future advancement of the field that is necessary to keep us not going into incrementalism will not occur. That's my concern. I have no problem with people going into chemistry or biology or something. The problem is they're going into doing, essentially money-making activity that's not necessarily at the foundations of knowledge.
Thank you. Does that answer your question, I guess? There is a question that may be closer to your heart. Do you think astrophysics affects particles even at the quantum level? Or astrophysics coexists alongside with particle at the quantum level? Okay. If so, as the space is expanding, will the calculation be affected decades down the road of space expansion? I don't understand the last part.
Okay, so almost certainly everything is connected through the equations of quantum field theory. We just haven't figured out how to link gravity in. Now, I could be wrong, and maybe they're not linked. So in some sense, absolutely, everything that I do ultimately ties back to the overarching quantum field theories that we think are there. But of course, just because things are linked, trying to understand the very big, that behavior of gravity and cosmology sort of emerges out of the quantum laws, but not necessarily in a way where you're going to think of it through quantum. In the same way as, you don't do artillery ballistic calculations using general relativity. Use Newton's laws because it's a much more straightforward way of thinking and doing those calculations. So absolutely, I think everything is in the quantum regime, but we probably won't think of a lot of what I do within astrophysics and within cosmology on that basis. Rather, we'll continue to work on the very foundations. For example, how does general relativity emerge out of quantum mechanics? That would be great. Not convinced that will happen in my lifetime, but gosh, it would be great if it did.
No, you are 50 years, so it will happen in your lifetime.
Well, I'm 55 now, so I think 45 and counting down. And if we have another year like the last, I'm not sure
Yang told me he wants to live till 106. I think he'll live longer than that. Get a new wife.
Yes, well, my current one would probably object.
No, I'm kidding. Sorry. Any question? If there are, your good friend Ping Koi Lam is here with us, listening to your talk.
Oh,
Professor Ping Koi
excellent.
Lam is sitting in the audience.
Hi, Ping Koi.
Any questions before we wrap up for the day? I know you're tired, but Brian is 8 o'clock at night. Am I right? Or 9 o'clock?
8 o'clock, 8:11 right now.
Yeah. Any questions?
But some of you, I will have the opportunity to interrogate some of you next week in person.
Oh, that's great. That's great. Yeah.
I look forward to that.
Oh, you have some question? Okay. You get the opportunity one day. Hongji, you asked me earlier on, any question from you now? Professor Fan Hongjing is going to ask you a question.
Okay.
Because he asked me a question this morning, and I said I have no question. Now he's going to do it. Yeah. We are waiting for the mic, so sorry about that.
Yeah, thank you very much for the very nice talk, very brain refreshing. So I'm the current director of the CN Scholar Program. As I mentioned in the morning, that there's a undergraduate student scholar program named after Professor Chen Yang since 2006. And a lot of scholars are attending online. So I wonder, do you have any words to our young scholars? Because they are studying different subjects, biology, physics, chemistry, and engineering, material science, and civil, everything. And the focus of the program is doing research, although only half of them will go to PhD, rest still go to industry. Do you have any words you want to share with them? Thank you very much.
Indeed. The luxury of having one of these scholarships, being able to undertake a program that includes research is one that I hope people relish. Research really needs to be enjoyed, but it's hard. When you start a research project, you're usually lost, and it takes a long time to sort it out. But if you have passion, you can work through that time when it's hard. But if you are able to persist, especially for those first couple of months, out of the fog, clarity starts to emerge. So I encourage people not to be worried too much if it all seems very difficult to begin with, because everyone I've talked to, with a few exceptions, has always had that sort of fog when they start their research projects. And to emphasize, it's really important for people to make decisions about what they want to do in life. And so while I lament my concerns about the future of physics and basic science, I should also say that it's not for everyone or even for most people. And people should be proud of what they decide to do, whether it be a PhD or whether they go in and work in industry and take that foundational work that they're doing, the research skills they have to go out and make the world a better place. And as long as people are always prepared to use their knowledge to make the world a better place, even if they're making money doing it, that's a good thing. But I always encourage people to think about, how am I making the world a better place? And do their best to always have that as an objective in whatever they do.
Thank you very much. Thank you.
Right, one last burning question before we end the session. No? There are lots of online questions, yeah, but all related to CN Yang and nothing on astrophysics, which Brian's would very much like to hear. Well, there's one, what can we expect our knowledge and understanding of astrophysics to be able to contribute to space tourism and at low and sustainable cost? I don't want to mention the last one. How would it benefit CN Yang and his family? Yeah.
So
sorry.
Space tourism is something we have to figure out how to, I guess, manage. People are going to want to do it, but we need to make sure that when we do it, we need to think of a way of it benefiting the world. And sometimes the technological breakthroughs necessary along to do something like space tourism, it's an impetus to make things happen. But I do think we need to make sure we think beyond just having it as being a plaything. We live on a planet that is, not getting any bigger. It's not accelerating with the universe, I'm sorry to say. It's very much bound by its gravity and other forces. So maybe getting the richest, most powerful people up in space and realizing it's not very big, the Earth, and that we're all going to have to live, all 8 billion of us, on it together successfully over the next 100 years. Maybe that is something that can come out of space tourism. But we do need to figure out how to live sustainably on our planet. And that is something that hopefully all of us will be thinking about no matter what we study and work on in the future. So probably one last question. What are your thoughts about the new telescope that has just been launched? The James Webb Space Telescope, JWST. This is going to allow us to do, I think, some really exciting things. We're going to be able to look back to the earliest stars in the universe and hopefully see how the universe was born roughly 13 and a bit billion years ago. Maybe we'll get an understanding of why there's all these black holes that are huge in the universe and how things came together. But in the very nearby universe, we're going to be able to look at the atmospheres of planets orbiting nearby stars and see what they're made out of. And wouldn't it be amazing if we see the signatures of some form of life in the atmospheres of Earth-like planets, or quite frankly, non-Earth-like planets. So it is going to create probably 20 years of amazing data. So if you're interested in doing astronomy, you're going to have a great machine there to help you do your discoveries, just like I had the Hubble Space Telescope when I was your age.
Thank you. I think we shouldn't hold back our distinguished guest too long. Let me also thank all the speakers for this afternoon session. Give them a round of applause, and thank you very much. And thank you, Brian, for the wonderful talk. And if you have not had your dinner, have a good dinner.
I'm ready for my dinner, and see everyone next week, hopefully one way or another.
Thank you.
Bye, everyone.
Thank you, Professor Kong and Associate Professor Craig, for chairing our afternoon session. And we hope that all our guests have enjoyed the talks and gained valuable insights from each of our speakers. We would now like to invite the Director of the Senior Scholars Program, Professor Fan Hong Jing, to give some closing remarks.
Good evening, everyone. It's a long day. I know it's very late, but I'm asked to make a wrap up. So I try to make it very simple because I myself is not in the really particle physics or astrophysics, but more on nanotechnology. So maybe I'm not the best person to comment about the great achievement by Professor Yang. But on general, in a very general remarks, I would like to say that first I want to thank everyone. The first thank you is thank all the distinguished speakers and guests for sharing your knowledge, your insightful, your very inspiring insights and your stories about the frontiers in science, as well as the scientific story and life story of Professor Yang. Okay, and as Professor Yang mentioned in the notes he sent to us, that he has enjoyed his life and he has lived a very happy and fruitful life, and he hopes we can benefit from what he has achieved before. So I think we all believe that Professor Yang has been a very creative scientist, physicist, and great educator, as well as a prominent intellectual. So he has set a very good examples, maybe very high examples to all of us for his seminal works for theoretical physics, but more important, his strong devotion to physics education. And I think I myself, I'm not able to get his level, but in terms of education, I try my best to learn from him. And because although we're in the different subjects, but I try our best to learn from him to be a good educators, because curate young generation for the future is very important for every university, for every lecturers, for every faculties like me. So this is the first thing, thank the speakers. And the second, thanks to the audience. Thank you for staying with us so late, and the guys here in the auditorium, as well as the guys online. And also thank you for very interesting, challenging questions sent to our speakers. I believe a lot of questions actually are very hard to answer. Yeah. So just now the interaction sessions were very brain refreshing and interesting. Okay, so this is the second thing. And the third thank you is thank all the organizing committees, the IAS, as well as the St. Yang office, as well as the sponsors. So without the hard work, today is impossible, right? So today is a golden opportunity for us to celebrate together the Professor St. Yang's 100th birthday, and also to feel the beauty of beauty of physics, the beauty of doing science, and the beauty of the synergy between science and arts. Because today Professor O mentioned the arts and Zhongguo Weiqi and the Chinese calligraphy, Chinese paintings. So he's also very interested on that part. Okay, and so this is the third thank you. And last thank you is thank to Professor Chen Yang himself. So thank him for his strong contribution to NTU, to Singapore, and to the whole world. Together, let's wish Professor Chen Yang a very happy and healthy 100th birthday. That's all I want to say. Thank you very much. Okay.
Thank you, you, Professor Fan, for your closing remarks. With that, we have reached the end of the Centennial Conference on Frontiers in Science in honor of Professor Xian Yang's 100th birthday. We hope that everyone has enjoyed today's conference and that our students present today have been inspired to continue to work hard to achieve their goals. Lastly, we request that all attendees to fill in the feedback form by scanning the QR code on the screen, and please also indicate in the form if you need endorsement for your attendance. Thank you once again for taking the time to join us today, and we wish everyone a pleasant evening ahead.